Okay, let's continue. Our next speaker is Strotmann, and she will speak about Poisson-Delaunay-Approximation.
Yes, okay. Hello, everybody. First of all, I would like to thank the organizers for this nice workshop and the opportunity to present some results. And today I want to present some results about the Poisson-Delaunay-Approximation, which is a joint work with my supervisor, Matthias Reisner, who sits over there. And, yeah. Okay. First, I would like to start with the construction of the Poisson-Delaunay tessellation. And as the name suggests, we need a homogeneous Poisson point process and in RD, and we call this point process ETT, whereby T is the intensity of the point process. And now there are two different ways to construct the Poisson-Delaunay tessellation, and one way of construction is using the well-known Poisson-Delaunay tessellation. And for the Voronoi cell of some point x of the point process, we take the set of all points which are closer to the point x than any other point of the point process. And the point x is also called the center of the cell, and the union of all Voronoi cells is called the Poisson-Delaunay tessellation. And now, when we want to construct the Poisson-Delaunay tessellation, we consider the set of all vertices of the Poisson-Delaunay tessellation. And we call the set of the vertices F0, and for some point x in the set F0, the Delaunay cell is defined as the convex hull of the centers of the Voronoi cells which have this point as a vertex. So, and again, the union of all Delaunay cells is called the Poisson-Delaunay tessellation, and yeah, you can see it here. And the center of the point x is called the center of the Delaunay cell. And yeah, as you can see in the picture, in comparison to the Poisson-Voronoi tessellation, it's possible that the center of the cell does not necessarily lie inside of the Delaunay cell. For example, this point here is the center of this Delaunay cell, and it lies outside of the cell. And moreover, as you can see in the two-dimensional picture, all Delaunay cells are triangles, and transferred to the d-dimensional case, all Delaunay cells have exactly d+1 vertices. And why this is the case becomes more clear with the second way of construction. And again, we consider a homogeneous Poisson point process, and we define for d+1 points from the Poisson point process, we define the ball having these points on its boundary. It's a d-dimensional ball, and since the points of the Poisson point process are almost surely in general position, this ball is uniquely determined. And yeah, now the Delaunay cell can be defined as the convex hull of a tuple of d+1 points of the Poisson point process when the ball determined by these points does not contain any further points of the Poisson point process. So, for example, these 3 points here in the picture, yeah, they form a ball, but since there are other points of the Poisson point process inside of this ball, these 3 points does not form a Delaunay cell. But, for example, these 3 points form a cell since the ball determined by these points does not contain any further points of the point process. Yeah, and again, the union of all Delaunay cells is called the Poisson-Delaunay tessellation. And yeah, as you can see here, both ways of construction lead to the same result. And the center of the Delaunay cells, which we have defined as the vertices of the Voronoi cell, are also the centers of the circumballs of the Delaunay cells, which is the reason why, of course, the distance of the centers of the Voronoi cells to its vertex is for every center the same. So it is also the radius of the circumball. Okay. Next, we want to use this tessellation to approximate a non-empty compact convex set K. And therefore, we take the union over all Delaunay cells with center inside of the convex set. And in the picture, you can see an example for the two-dimensional approximation of an ellipse. And the union of all these red-colored cells is the approximation of this set K. And yeah, the red-colored cells are exactly those cells with center inside of the convex set K. So, for example, this cell here belongs to the approximation because the center of the cell lies inside of the ellipse. And for example, this cell here does not belong to the approximation because the center of the cell lies outside of the convex set K. Yeah, and in the following, we are now interested in the volume of the approximation, whereby VD denotes the d-dimension in the back measure. And yeah, our first result now shows that the volume of the Delaunay approximation is an unbiased estimator for the volume of the convex set K. Yeah, the proof results of some straightforward computations and the translation invariance of the back measure, so it's not that interesting, but we can see that the expectation of the volume of the approximation is equal to the volume of the set K. Okay. And before I will present you some other results, I would like to give you a short overview of the known results for the Poisson-Delaunay approximation. The construction is quite similar, but of course we take the Delaunay cells with center inside of the convex set and not the Delaunay cells. And yeah, there are many publications about the Delaunay approximation, and first there are some results about the variance and the upper bound, which you can see here, which is some constant depending on the dimension t times the intensity of the point process to the power -1 over d times the surface area of the convex set. This is upper bound was firstly proven by Heveling and Reitzner in 2009, and a few years later Schulte was able to compute a lower bound of the same order, and again a few years later the asymptotic of the variance was calculated. And there also exists a central limit theorem, and the convergence rate is the central limit theorem when the intensity goes to infinity, so the intensity of the point process increases, and the convergence rate is -1/2 + 1 over 2t. And there are much more results, like for example some considerations according to the symmetric difference or some concentration inequalities, and so on. And now we were able to find some quite similar results for the Poisson-Delaunay approximation. And our next result is about bounds for the variance. And as you can see, the bounds here have the same order than the variance bounds of the Poisson-Delaunay approximation. And in the following, I would like to give you an overview of the main ideas of our proof for that. Okay, and therefore I will start with the proof of the upper bound, and for the upper bound, we use the Poincaré inequality, which gives an upper bound for the variance of some square integrable Poisson function. And therefore, we have to approximate the difference operator, and for that, we have to answer the question how the volume of the approximation changes when we add one additional point x to the Poisson prime process. And first, we can note that the additional point x affects only those cells which contain the point x in its circumball, because we know d+1 points of the Poisson point process form a Delaunay cell when there's no further point of the point process inside of this ball. So when we add the point x, all cells change which contain the point x in its circumball. And in this area, new cells are formed which have the point x as a vertex. And what we can see is that the area which is affected by this point x is restricted to some ball with some radius rx. And another important fact is that for the approximation we consider only those cells which have its center inside of the convex set K. So when the hole by the point x affected area lies completely outside of the set K, the approximation does not change at all. And the same applies when the hole by this point x affected area lies completely inside of the convex set K. Because when all old and all new cells belong to the approximation does not change at all. So we need some additional limitation that the point x has to be near the boundary of our convex set K. Because then the convex set intersects the by x affected area. And all this then lead to the following upper bound for the first difference operator, and thereby kappa d times rx over d is the volume of the d-dimensional ball with radius rx. And this is the indicator function which adds the additional limitation that the point x has to be close enough to the boundary of the set K. Okay, then since we need the square of the difference operator, it doesn't matter if the operator is positive or negative, so we can consider the absolute value and then we can insert it to the Poincaré inequality. And with some computations, I don't want to go into detail on that, we finally get an upper bound for the variance. Okay. For the lower bound, which was a bit more complicated, we used the theorem by Matthias Schulte and Vanessa Trapp. And this theorem gave us, under a certain condition, a lower bound for a square integrable Poisson functional, which is a factor depending on some constant alpha times the integral we have already seen as the upper bound for the Poincare inequality. And to apply this theorem, we first have to check the condition here above. And we start with an upper bound for the left-hand side of this expression. And since we already have an upper bound for the first order difference, it was not so difficult to compute an upper bound for the second order difference. We just have to add this additional limitation that the point y has to be close enough to the point x. And yeah, we can again insert this to our expression we want to calculate, and the calculations are quite similar to the calculations for the upper bound, and again we get some constant depending on the dimension in the convex set k times intensity to the power -1 over d. Okay, next we need a lower bound for the right-hand side of this condition, and since we already know that the difference operator is equal to 0 when the distance of the point x and the boundary of k is too large, we restrict our considerations to some small area near the boundary of k. And therefore, we assume that our point x we want to add lies in some set m epsilon. And m epsilon is defined in such a way that it contains only those points outside of the convex set k which are have a distance towards the boundary of k which is smaller or equal to epsilon half. And thereby epsilon is some small constant depending on the in radius of the convex set k. Okay, and we are allowed to make this restriction because we can split our integral into two parts. So we first integrate over the set m epsilon and then over the complement of it. And since we integrate over the square of the difference operator, we can just drop this second summand and still get a lower bound for this expression. Okay, now we have restricted the area where the point x can be located, but we still don't know if the volume of the approximation increases or decreases. And it can even happen, as you can see in the next picture, that the additional point x decreases the volume of the approximation and increases the volume at the same time. And this is a problem, and to avoid this problem, our idea was to construct some situation. We will call this situation E, and so that in this situation, a volume change is only possible in one direction. And before I want to tell you how we constructed this situation, I would like to show you why this is helpful for us, because with the law of the total expectation, we can split the expectation of the squared difference operator into a sum with two parts. And first we have the expectation under the condition that our situation E holds, and additionally we have to multiply with the probability that this situation E occurs. And we don't know how the difference operator behaves when the situation E is not true, but it doesn't matter at all because we have the expectation of the squared difference operator. So we can again drop the second part here and get a lower bound, and we only have to calculate the expectation of with the condition that our situation E is true times the probability for that. Okay. And now I want to show you how we constructed this situation E, and in this talk I will restrict the construction to the two-dimensional case, and over I will leave out all exact numbers and distances. I just want to give you a rough idea on it. And yeah, as you can see, this gray part here is the set k. The narrow stripe next to the boundary of k is the set m epsilon, and the point x, the red point, is the point x. The first step is we construct three balls around the point x, all with the same radius. Two balls lie outside of the convex set k and one point is inside of the set. And now we assume that each of these balls contains exactly one point of the Poisson point process. And furthermore, we assume that except of these 3 points, there's a large surrounding of the point x where no further point of the point process is located. And with this construction, the 3 points form a Delaunay cell with center inside of the convex set K. And since we have chosen this area where no further point is located extra large, the additional point x affects only this cell you can see in the picture. And now 3 new cells are formed which have the point x as a vertex. And since the old cell before belonged to the approximation, since the center lies inside of the convex set, now at least this red part, so this cell has its center now outside of the convex set. So the volume of the approximation at least decreases by the volume. At least decreases by the volume of this red cell. So we can approximate the expectation under the condition that our situation we have constructed is true. The expectation can be bounded from below by the square of the volume of this red colored cell. Okay, then we only have to insert our results, and what's still missing is the probability that the situation E is true. But since our Poisson point process is homogeneous and fulfills the property of complete independence, it's not that difficult because the probability that, for example, each of these balls contains exactly 1 point of the Poisson point process does only depend on the volume of the ball and the intensity of the point process, but not on the location of the ball and not on the number of points in the surrounding of the ball. So it's not that difficult, and I don't want to go into detail on that, but what we know is that both factors here does not depend on the point x anymore. So we can extract both from the integral, and what stays is the volume of the set and epsilon. Okay, and we can compute it, insert the results, and then we get a lower bound of the order -1 over d, and again multiplied with some constant depending on the dimension and the convex set K. And now the condition of the theorem by Trapp and Schulte is fulfilled when we choose alpha as the fraction of the 2 constants. Then the condition is fulfilled and we can insert our results and finally get a lower bound for the variance. Good. Next, we use the variance bounds and especially the lower bound to calculate a central limit theorem. And the order of the convergence rate here is the same as the convergence rate for the Poisson-Delaunay-Approximation. And yeah, I don't want to go into much detail on the proof, but I just want to show you which theorem we use for it. We use the theorem by Lars, Pecati, and Schulte from the year 2015, and it's somehow a combination of the Variablen-Stein method and some bounded moment condition. Yeah, so in our case we choose P1 and P2 equal to 1, so we had to bound the fifth moments of the first and the second difference operator, and since we already have upper bound for both, it was not so complicated. And nice of this part is that we only integrate over the probability that the difference operator is non-zero, and this is quite nice to calculate. Yeah, but it's not so interesting and I don't want to go into detail on that. And instead I would like to use the last few minutes to talk about the symmetric difference. And the symmetric difference of the Poisson-Delaunay approximation is defined as the volume of the area parts inside of the convex set which do not belong to the approximation and the parts outside of the convex set which do belong to the approximation. And it's quite obvious that when the intensity of the point process grows, that then the volume of the symmetric difference decreases. And the same should hold for the expectation of the symmetric difference. And in the following, we are interested in the asymptotic behavior of this expectation, and therefore we got this following result, that for every Borel set with bounded volume and bounded perimeter, the expectation of the volume of the symmetric difference behaves asymptotically, lies a constant depending on the dimension d times the perimeter of the set K times intensity to the power -1 over d. And the definition of the perimeter is a bit technical and I don't want to define it now, but what I can say is that for example, convex sets, the perimeter is equal to the volume of the boundary. So for convex sets, we can exchange this by the volume, also d minus 1 dimensional Hausdorff measure of the boundary. And yeah, unfortunately, we were not able to calculate this constant CD exactly, but there exist quite similar results for the Poisson-Delaunay-Approximation by Reisner, Spodarev, and Sapporo sets from the year 2012. And they were able to calculate this bound exactly, and when you compare these two bounds, you can see that they only differ by this additional factor E. And we're not sure, maybe this is a factor of the approximation we had to make, but we can't say that for sure. But at least we can see that the asymptotic behavior is for both approximations quite similar. Okay. And now I see I was a bit fast, but I'm at the end and I would like to thank you.